Welcome to our seminar. It's my great pleasure and honor to introduce Dick Gross. I've known Dick for a long time, maybe a little over 50 years. I want to say just a few things about him. First of all, he got his PhD in 1978. His thesis advisor was John Tate. He wrote, his initial interest was in elliptic curves with complex multiplication. He wrote a well-known Springer lecture notes on that subject. It was been quite influential. But I wanted to comment on something that he wrote before he finished his thesis that played a significant role in my career, namely his work on the Challis-Selberg formula. And while he was still a student, he wrote a very significant paper on the Challis-Selberg formula, a formula that at that point only had an analytic proof. He found a remarkable geometric proof of the formula. And this proof really transformed the entire subject. Not many people know that this proof inspired Deligne for this development of his theory of absolute Hodge cycles. And in turn, the theory of absolute Hodge cycles enabled Deligne to prove a vast extension of the Shimura-Taniyama theory, which enabled eventually, actually not eventually, quite quickly, others to complete the construction of a general theory of Shimura varieties. This was a very significant thing coming out of a paper of Dick's while he was still a graduate student. Now, after that, of course, there's the well-known, in the 80s, he produced with Don Zagier, the Gross-Zagier formula, another transformative accomplishment in number theory. And in that period, he also won the Cole Prize and got a MacArthur Award. And then in the next decade, he created the conjecture of what is called the Gross-Prasad conjecture at the time. I guess now it's called the conjecture of Gan, Gross and Prasad. Gross-Prasad conjecture, which also gave rise to an industry of work. I guess he's going to talk to us about that today. It's a great honor to have him, and I want to thank him for the wonderful influence he had on my career in several ways. But as he knows, I wrote my thesis on the same topic that the same type of family of abelian varieties that he used in his famous paper on the Challis-Selberg formula. And it's one of the first papers I ever read, and it had a lot of influence on my own research. So thank you.
Thank you, Don. That was very, very kind introduction. I'll say that I did work on the Challis-Selberg formula when I was a graduate student, and I went to this very interesting conference. Took place in Corvallis, Oregon. It was introducing all of us graduate students to the Langlands program, but unfortunately, all the experts in the Langlands program were there, and so they just spent the whole time talking to each other. We were completely lost. And at one point in the conference, Jean-Pierre Serre, who knew about this thing I had done on Challis-Selberg, wanted me to meet Deligne and explain to him what I had done. So I sat down with Deligne, and at this time I was still looking for a thesis. And I said to Deligne, I found a geometric proof of the Challis-Selberg formula, and Deligne smiled and looked at me and said, oh, have you also proved the Hodge conjecture? And I said, no, I think I have, but if I have, I'd like to know about it because that might be a thesis for me. And then Deligne explained, I explained what I had done, and he said, no, you haven't really proved the Hodge conjecture, but maybe something will come out of it. And so that became, as Don said, his great work on absolute Hodge cycles on abelian variety. Anyhow, to this talk. So let's see if I can get this to work. Uh-oh. Here we go. These are my two collaborators on this project. This is Teck Gan and Dipendra Prasad. Teck is currently at the National University of Singapore, and Dipendra, who was at Tata for many years, is now at IIT Mumbai. So I know this is a chat talk, but I thought what I would do is first describe what the conjectures are in brutal detail, in broad strokes, to get an idea what these things are about. And then maybe at the end of the talk, if there's time, I'll spend a little time about how we came about them. So there are these three all interlinked conjectures. There's something called the local case, and that extends branching laws for representations of compact Lie groups. So that's really a problem in representation theory, a famous problem, which I'll spend a lot of time on. And then after the local case comes what's called the global case, which extends a beautiful formula that was shown to me by Jean-Luc Valls-Perget. And finally, once we get the global case, I'll talk a little bit about the arithmetic case, which is the most interesting to me, which extends the formula I found with Don. So if you, as I said, I can only do broad strokes in an hour, but if you want to read about the whole precise conjectures, the three of us, Gan, Prasad, and I wrote a volume, 346 of asterisk, where they're all laid out, and that would be with a lot of background material on the Langlands, correspondence, etc. And I recommend that. Okay, so let's start with a picture. So this is a famous picture. You find this in math books, chemistry books, physics books, etc. And first, I'm going to try to explain what this picture is trying to represent. It's an effort to illustrate the theory of what are called spherical harmonics. So spherical harmonics began with Pierre Laplace's decomposition of the functions on the two-sphere. The two-sphere are the points in 3 space of distance 1 from the origin, or where the coordinates x squared plus y squared plus z squared are 1. And that's not just the functions on the two-sphere are not just a vector space, but they carry a linear action of the special orthogonal group, because the two-sphere is an orbit for the special orthogonal group, the linear transformations preserving the inner product. And so that acts on the functions on the two-sphere by composing a function with one of these orthogonal transformations. And when you're given a natural representation of a group like this, you want to decompose it into its irreducible pieces. And Laplace found those irreducible pieces. That's the decomposition of this function space. So to describe them, we'll let WL be a vector space of homogeneous polynomials of degree L on R3. So that's a finite dimensional vector space with basis the monomials of degree L. We don't take all of them. We take the ones which are annihilated by this second order differential operator that's now called Laplacian. Those are called harmonic polynomials. Now, if you take the space of polynomials of degree 0, that's just the constants. That's a one-dimensional space. They're all annihilated by the Laplacian. If you take the polynomials of degree 1, they're spanned by x, y, and z. That's a three-dimensional space. And they're clearly all annihilated by the Laplacian because they're linear. But if you go to the quadratic polynomials, it's a 6-dimensional space, but only a 5-dimensional subspace is annihilated by the Laplacian. And the reason that this becomes a representation, this kernel of the Laplacian becomes a representation of the group SO3, is that this differential operator is invariant under SO3 if you take x, y, and z to be an orthonormal basis of 3 space. And what Laplace showed was that this is an irreducible representation of SO3. There are no stable subspaces except 0 in the entire space. Its dimension is 2L plus 1, where L is the degree of the polynomial, so 1, 3, 5, 7. And this is the big thing, that the functions on the two-sphere are in some sense decomposed as a direct sum of these irreducible representations, each with multiplicity 1. Now, it depends which functions you take. If you took polynomial functions, it would be an actual algebraic direct sum. Every polynomial function could be decomposed uniquely as a linear, a quadratic, a constant, a component, and most of them would be 0. If you took square integrable functions, this would be a Hilbert direct sum where you could use an infinite number of the components tending to 0. Okay. Now, it turns out that these are the only irreducible representations of SO3, so they all occur with multiplicity 1 on functions on the two-sphere. Well, Laplace did more. He analyzed the decomposition of these representations when they were restricted to the subgroup of the orthogonal group fixing a point on the two-sphere. So that subgroup consists of all the rotations around the axis orthogonal, the rotations around the axis that goes through that point, which on the orthogonal plane is just the group SO2, or the complex numbers of absolute value 1 under multiplication. And it turns out that if you take these irreducible representations on the harmonic polynomials of degree L, and you restrict them to this abelian subgroup, its irreducible representations all have dimension 1. And the characters that occur are exactly the mth powers on the unit circle, where m runs from minus L to plus L. There are 2L plus 1 such integers. And so this restriction is also a multiplicity free. And that is somehow how you explain, let's see if this works. I don't seem to be able to get this. Let's try this. That's this picture. This picture is the trivial representation, the 3-dimensional, the 5-dimensional, the 7-dimensional representation decomposed into lines, which are the eigenspaces for this abelian subgroup of SO3. And the colors even have meaning as to whether the specific eigenfunction on that line is positive or negative, et cetera. These eigenfunctions are incredibly beautiful and are called spherical harmonics, and you can find formula for them in the literature, and they're also quite useful in astronomy and chemistry and physics, et cetera. Okay, now there's a similar result, much more complicated, and only it's a 20th century result, that when you try to restrict irreducible representations of the compact group SO2n plus 1 to the subgroup SO2n that fixes a point in 2n plus 1 dimensional vector space. So the orthogonal complement, it acts on the orthogonal complement, which has dimension 2n. And to describe that formula, I have to tell you how you parametrize representations of these compact Lie groups. And usually the people like to parametrize them by the highest weight, and that's the theory of Cartan and Weil. But Harishchandra actually found a slightly better way of parametrizing them using what's called the infinitesimal character, which is the highest weight plus the vector rho that lies in that particular Weil chamber. And for the representations of SO2n plus 1, the Harishchandra parameters are half integers. That means not integers, but half integers, alpha 1, alpha 2, up to alpha n, which lie in this cone. And for example, if you take SO3, you only get one of these half integers, and the dimension of the irreducible representation is 2 times that half integer, which is these odd numbers. Similarly, the irreducible representations of SO2n are indexed by their infinitesimal characters. And in this case, the infinitesimal characters are given by integers in a cone. And beta n can be an arbitrary integer, but the others have to be positive. And for example, for SO2, we saw the possible characters are just all possible integers. That's beta n. Okay, so the famous restriction formula, which is called the branching formula in the literature, which was initially discovered by physicists, is this following restriction formula. When you take one of these W alphas, which is an irreducible representation of SO2n plus 1, and you restrict it to the subgroup SO2n, it's a direct sum of these U betas, irreducibles, where there are a finite number of betas, and they're the ones that interlace between the alphas. So beta 1 has to be an integer between the half integers alpha 1 and alpha 2, and beta 2 has to be an integer between the half integers alpha 2 and alpha 3, etc. So in the previous case, SO3 to SO2, there's only one alpha, and the inequality is simply that alpha is greater than the absolute value of beta. And that works with the infinitesimal characters. Now, the key thing for us, which we're going to need as we go on, is that this restriction is multiplicity free. Namely, these irreducibles that occur with multiplicity 1. That's an important fact about this restriction problem. Usually when you do a restriction problem, you get higher multiplicities. And you can state that in the following way, that the homomorphisms as modules for SO2n between U and W, which is the same thing as the homomorphisms for the tensor product of W and its U dual to the complex numbers, which are invariant under SO2n, has dimension less than or equal to 1. It has dimension 1 if U occurs in the restriction of W, and it has dimension 0 otherwise. And we see the dimension is 1 if and only if the betas and the alphas branch in this way on the bottom of the slide. Now, later on, people started to try doing restrictions of orthogonal groups that weren't compact, but still real groups. So for example, there's a famous restriction formula for the hyperbolic orthogonal group of signature 2n1. It has a discrete series representation. That's like the finite dimensional representations of the compact group, but it's infinite dimensional. And its restriction to the subgroup fixing a negative line, which is now a compact group, is given by a similar branching formula. It's an infinite sum of irreducible representations with multiplicity 1. and the corresponding indices, beta, are now branched in this way. That's the famous Blattner formula for this discrete series. Notice that there are an infinite number of possibilities for beta because beta 1 is just an integer, an arbitrary integer bigger than alpha 1. So an important theorem, which was first shown to me by Joseph Bernstein and proved by some of his students, is that for any irreducible representation of the odd orthogonal group, its restriction to the subgroup fixing a line is always multiplicity free. And that works for groups over the reals, over the complex numbers, and over p-adic fields. So that's a general theorem that this dimension of this space of homomorphisms from an irreducible of SO2n to an irreducible of SO2n plus 1 has dimension less than or equal to 1. And the main problem that the local conjecture that I made with Teck and Dipendra addresses is when is the multiplicity 0 and when is the multiplicity 1? In other words, what is the analog of this branching formula that tells us exactly which representations of SO2n occur in this restriction problem? So that's a purely a problem in representation theory. And as you could say that it began with Laplace's description of the restriction from SO3 to SO2. But to answer this problem about which representations occur in the restriction, we are going to need to leave the harmonic analysis in Laplace's great Mécanique Céleste. There's Laplace, there's the cover page of his item, and we're going to have to go to the harmonic analysis in John Tait's PhD thesis, which is entitled Fourier Analysis in Number Fields and Hecke Zeta Function. And one of the great PhD theses ever written in mathematics. If you ever wanted a good introduction to modern number theory and you want to read something that's just beautifully written, I cannot recommend this anymore. So what did Tait do in this? So what are these Hecke Zeta functions? Well, the Hecke Zeta functions that we're going to study are generalizations of the Riemann zeta function, which is given initially by Euler as this famous Euler product over the primes. And then Euler realized that if you completed it using his newly invented gamma function, and you called it zeta star of S, that it could be extended to the complex plane and satisfies this famous functional equation. Now, Euler only proved that functional equation when S was an integer. Riemann was the person who proved it in general. Now, these Hecke L functions generalize this in the following way. You start with a number field, not just the rational numbers, and you study its ring of Adels and its group of Edels. So the ring of Edels is a great idea that was introduced by Chevalier and Weil, and it consists of the product of all of the completions of the number fields at all of the valuations. Now, you can't take the direct product. That's a nice thing to do, but it's too large. It's no longer a locally compact ring. And you can't take the direct sum because that's too small. It doesn't contain the number field embedded diagonally. But if you take what's called the restricted direct product, where almost all the entries in any Adel lie in the ring of integers of the local field, then that has the property that it contains the number field is diagonally embedded and is also locally compact. And its multiplicative group of that ring are called the Edels. And they're also a restricted product now of the multiplicative group of the local fields. And a Hecke character turns out to be a homomorphism from the Edels to the complex numbers, a group homomorphism, which is trivial on the diagonally embedded field multiplicative group of the field. And such a character is a product of local terms, chi v, where each one of those is a character of the multiplicative group of the completion. And almost all of those characters have to be unramified, namely trivial, on the units of the completion. And the L function of a Hecke character, which is what Tait studies in his thesis, is defined like the Riemann zeta function as a product of local terms. And in the case of the Riemann zeta function, the character is the trivial character. The Euler product gives the local terms at the prime p, and this gamma function turns out to be the local term at the place infinity of the rational numbers. This L function, this Euler product, like the Riemann zeta function, converges in a right half plane. And like Riemann, Hecke had proved the analytic continuation and a functional equation for this L function, which Tate reproves in his thesis using a slightly different method. And it's more complicated than the functional equation of the zeta function in that there's an exponential term, this A of chi, which has to do with the ramified primes of the character. And there's a constant, which is called the local constant or the global constant. And what Tate did in his thesis, which was really novel, many novel things, but one of the things he gets is that the local constant in this functional equation factors into terms associated to the local characters, just like the L function factored into local terms. And the local terms satisfy that if you take the constant of chi v and the constant of its complex conjugate, then that's the value of the character at -1, which is either plus or minus 1. And now I should say that the way this was generalized is to view the characters of these multiplicative groups of the completions as characters of what's called the Weil group of the field. So that's the beginning of local class field theory. And the Weil group is a non-abelian group whose abelianization is exactly the multiplicative group of the field, and it's related to the Galois group of the algebraic closure of KV. So I'll tell you what these Weil groups look like, because we're going to need them later on. Over the complex numbers, the Weil group is just the multiplicative group of the complex numbers. For the real numbers, the Weil group turns out to be the normalizer of the complex numbers inside the multiplicative group of the quaternions. So that's got two components, C star and C star J, but it's not a semi-direct product. And over the p-adic fields, the Weil group is the subgroup of the Galois group of the algebraic closure, which on the unramified extension acts as an integral power of the Frobenius automorphism. So this was a big discovery that they made that found a group for each local field, defined really in terms of extensions, which had the property that it calculated a lot of the Galois group in it, but its abelianization was exactly the multiplicative group of the local field. Now, Deligne defined these local epsilon factors for higher dimensional representations of the Weil group. For one-dimensional representations, let's see, for one-dimensional representations, that's the same as for characters of the multiplicative group of the local field. The epsilon factors had been defined by Tate. But Deligne showed how you could also define them for higher dimensional representations. And the generalization of that formula about the factor of chi v and the factor of chi v bar was that if you took the product of the epsilon factor of one of the higher representations and the epsilon factor of its dual, you got the determinant of the representation, which is a one-dimensional representation, evaluated at -1. And when you think of the one-dimensional representation, you should think of it as a character of KV star.
Can I ask a question?
Please.
So I'm wondering is there any uniform definition of the Weil group?
Absolutely. That's exactly what Weil did. Namely, he used all of local class field theory in terms of to give the definition of the Weil group as an extension of the multiplicative group of extension fields by the Galois group of that extension field, and then pass to the limit. And I'm just telling you what turns out to be the answer in the end. But the definition is completely uniform, and but it's just much too complicated to go into in this talk. Okay. In any case, Deligne had defined these things for higher dimensional representations of the Weil group, and they satisfied this identity. So a natural case of those representations would be to see what happens when the representation is self-dual. So if it's self-dual, that the left-hand side becomes epsilon of m squared, right? And m dual is the same as m. And then self-dual representations have determinant, which is either a trivial representation or a quadratic character. But suppose the determinant's trivial. Then it says that epsilon of m squared is 1. So the local constant associated to a self-dual representation with trivial determinant has to be plus or minus 1. And Deligne worked out in the orthogonal case, self-dual would be either an orthogonal pairing or a symplectic pairing. In the orthogonal case, the sign has a beautiful interpretation as to whether the representation which goes into the special orthogonal group, if it's self-dual with trivial determinant, lifts to the double cover, the spin group. Basically, it lifts if the epsilon factor is +1. It doesn't lift if it's -1. So that's a great interpretation. But when the representation is symplectic, so preserves an alternating form, then it does have trivial determinant. So the sign is plus or minus 1, but nobody really understood the sign. And those signs come up all over the place in number theory. For example, if you study the L function of an elliptic curve, that's a two-dimensional symplectic representation. And if you want to know the global epsilon factor, you want to know the local epsilon factors, which are these signs, and they determine a plus or minus 1 in the functional equation, which tells you whether the function vanishes to even or odd order in the center of the critical strip. And that's important in the conjecture of Birch and Swinnerton and Dyer. So number theorists are very interested in these symplectic epsilon factors, but they become quite hard to compute. So what's amazing is that the local conjecture I make with Gan and Prasad relates the branching laws when you restrict from SO2n plus 1 to SO2n to the signs of these symplectic epsilon factors. So I should emphasize that in a lot of these dictionaries in mathematics where one problem is a problem in representation theory. The other problem is a problem in number theory. Now you shouldn't think that our conjecture solves either of those problems. It just says, if you could solve the problem in representation theory, you would know what the epsilon factors were. And conversely, if you knew what the epsilon factors were, you could solve the restriction problem. Still, it's a cool interaction of the two subjects. And I want to at least give you a statement of it. Now, to actually relate these two subjects, we need to use a very important bridge that was constructed between them, between representation theory and number theory. That was the vision of Robert Langlands. This is his famous Yale lecture notes on Euler products. One of the great ideas, in my opinion, in mathematics of the second half of the 20th century. And what Langlands did was he realized that the names of the irreducible representations of the odd orthogonal group were just given by these symplectic representations of the Weil group, whose dimension was 2n, if you wanted to do orthogonal group 2n plus 1. Those are called Langlands parameters. And similarly, the names of the irreducible representations of the even orthogonal group are parametrized by orthogonal representations of dimension 2n, where the determinant of the orthogonal representation is the discriminant of the quadratic space. So this is really shocking because it just, the names of the irreducible representations, that's a fundamental problem in representation theory. And here it brought in not just some concept from number theory, but one of the central concepts in number theory. So it was a great connection. Now, if you think about this, we should be able to redo the real theory of highest weights or infinitesimal characters should be able to be re-expressed in terms of these Langlands parameters. And for example, let's consider these representations of the Weil group of R. Now, remember, I told you the Weil group of R is the normalizer of the complex numbers in the multiplicative group of the definite quaternions. So that contains the multiplicative group of complex numbers with index 2. And so we can make two-dimensional representations of the Weil group of R by inducing characters of the multiplicative group of the complex numbers. And here I take z over z bar to the 8th power. That actually makes sense if a is a half integer, if you think about it. And the parameter of the irreducible representation that I call W alpha, where I had alpha 1 greater than alpha 2 greater than alpha 3, all half integers, is the direct sum of n of these two-dimensional representations, J alpha 1, J alpha 2, which are all symplectic. So it gives a symplectic representation. And the parameter of the irreducible representation I called U beta is a direct sum of n orthogonal representations. So you can redo the whole theory of highest weights of Cartan and Weil for compact real groups in this language of representations of the Weil group of R, because there's some particularly simple two-dimensional representations of that Weil group. For the p-adic groups, There aren't such simple representations of these groups, and these were completely new names for representations. Okay, let's accept this parametrization of Langlands, which is now a theorem, but at the time that Prasad and I started working on it, it wasn't a theorem at all. It was just a conjecture, but we were willing to go with it. So in fact, these representations M and N, one symplectic, one orthogonal for the Langlands parameters, they actually don't just parameterize one representation, but a finite set of irreducibles called an L packet. And the elements of this L packet are indexed by a beautiful thing. They're indexed by irreducible representations of the component group of the centralizer of the parameter. So if you have a homomorphism into this product, a symplectic group and an orthogonal group, you can take a look at the image and you can see what centralizes it. And that's a reductive complex group. And you can take its component group, which is a finite group. And in our case, it's an elementary abelian 2 group, because it turns out the centralizer by Schur's lemma is a product of general linear groups and symplectic groups and orthogonal groups. And they're all connected except for the orthogonal groups, which have 2 components. So the full centralizer turns out to be an elementary abelian 2 group. And consequently, an irreducible representation is just a homomorphism from the centralizer to plus or minus 1. Okay, so here's the conjecture. It says that in each one of these L packets, well, you have to take a certain type of L packet called generic. There's a unique irreducible representation of the product group, SO2M plus 1 cross SO2N, such that the dual of U occurs in W, or such that the dimension of this Hom space is 1. And for all the other representations in the L packet, the dimension of the Hom space is 0. So that solves, in some sense, the restriction problem, if you could say which was the unique representation. Well, to give the unique representation, you need to give a quadratic character of the component group. And here it is. If you take an element A in the centralizer in SPM, and an element B in the centralizer in SO2N, and you use the symplectic epsilon factors of the part of M where A is minus 1 tensored with N. So that's a symplectic tensor orthogonal representation. So it's symplectic. And then there's a little determinant factor. And here you use the part of the symplectic representation, which is M tensor, the orthogonal representation where B is minus 1. So this looks like a complicated formula, but it's giving the dimension of this Hom space in terms of symplectic epsilon factors. Not that they're easy to compute, but nonetheless, that's the recipe we predicted. This is now known to be a theorem. I'll get there in a moment. And so in particular, which is important, if you look at the center of this group, so that obviously centralizes any parameter. So minus 1 is in the center of SPM and minus 1 is in the center of SON. And the value of this character on both central elements is just the symplectic epsilon factor of the tensor product times this determinant. And that turns out to determine which orthogonal group actually is acting on these various representations. Okay. Now, if you look at the real orthogonal groups and the so-called discrete series L packets, then the epsilon factors are determined by the branching of the infinitesimal characters, and we retrieve all of the old branching formulas in the literature. So one of the great achievements, in my opinion, of the last 20 years in representation theory is that Jean-Luc Waltz-Purgé proved this entire conjecture with all the epsilons, et cetera, for p-adic orthogonal groups in 2010. I recounted the story that I was giving lectures on these conjectures in Paris at the time. Waltz-Purgé invited me politely into his office, told me he had proved them all, started to show me the proof. It was so astounding that I began to question whether I was understanding his French. But after Waltz-Purgé did this, there was an explosion in the subject. The last 10 years must have seen 500 papers written in this, and all based on his wonderful ideas, and which won him, among other things, a Clay Research Award. So I'm now going to pass on to the global conjecture, which is not exactly about symplectic root numbers, but instead about the L functions. So the global conjecture is based on the local ones, I should say. It starts with a number field. It takes the product of the odd orthogonal group and the even orthogonal group over the number field and takes the subgroup SO2n embedded diagonally in both. So that's the fixer of a vector in the 2n plus 1 dimensional space and embedded by the identity map into the second factor. And we let A be the ring of Adels, and we let W tensor U be an irreducible representation of the Adelic group, which embeds in the space of automorphic forms. So you need a homomorphism from this representation into the functions on the Adelic group, which are left invariant by the rational group. Now that's a generalization. This space of automorphic forms is a generalization of what we call the Hecke character. If you take the functions on the multiplicative group of the Adels modulo the multiplicative group of K, that decomposes as the direct sum of all the Hecke characters. Okay, now if you have that, you can take an automorphic form on this group and integrate it over this coset space, which is embedded diagonally. And that gives you a linear form from the function space, which is invariant under the Adels of the subgroup. But the question is, when you restrict this form to the subspace W tensor U, is it non-zero or not? It turns out that the space of linear forms invariant under HA on W tensor U has dimension 0 or 1, because a necessary condition for this restriction to be non-trivial is that there has to be an invariant homomorphism. And the invariant homomorphisms on this tensor product decomposes a product of the invariant homomorphisms on the local groups, and we've seen that those dimensions are either 0 or 1. So it has to be 1 for all the local completions. And that's the sort of thing that's decided by the local conjecture. So every one of these local completions has to be the distinguished element in the L packet where the dimension of the space of homomorphisms is 1, not 0. Otherwise, if you took this linear form and you restricted, since it would be HA invariant, it would have to be 0. So let's assume that all these local conditions are met, that we have linear forms locally for every V, and we have a specific test form that we want to ask about globally. Is it non-zero in this one-dimensional space? Well, since it's locally non-zero, then we find that the Hasse-Witt invariants of these spaces are given by this epsilon factor, and consequently, since we started with global orthogonal spaces, the product of these Hasse-Witt invariants has to be 1 by Hilbert reciprocity. And since the product of these determinants is always 1, it says the product of these local epsilon factors of the tensor product representation has to be 1. Well, that's good, because that means that that's the sign in the functional equation of the tensor product L function, which is like the Hecke L function given as a product of local terms. So since the sign in the functional equation is +1, that says in the center of the critical strip, it vanishes to even order. And the global conjecture says that the diagonal period integral is non-zero when we restrict to this subspace of automorphic forms, if and only if the value is non-zero, namely if it vanishes to order 0, the minimum even order. And in fact, there's a formula for the value of the tensor product L function in the center of the critical strip in terms of these diagonal period integrals. Okay, now I should say that actual formula is still a conjecture, but just as we've done restriction for orthogonal groups, you can do restriction for unitary groups. This is something that Teck pressed on us later in the conjecture. And if you do restriction from UN to UN minus 1, you get a similar conjecture. And in that case, the tensor product L function, this L of M tensor N, is what's called a Rankine L function over the quadratic extension field. And that's a well understood L function. Its functional equation is known. There's an integral representation for it. So you can actually try to attack this global conjecture. It's hard, but you can attack it. Whereas in the orthogonal case, we have no idea what to do. And in fact, Wei Zhang has made tremendous progress on this unitary case using what's called a relative trace formula discovered by Jacquet and Rallis. Here's a picture of Wei. So he was recently awarded, I believe last year, the Clay Mathematics Prize for this achievement. And since his work, there's been even more done. So one can say that the local conjecture is understood in both the orthogonal and unitary case, and the global conjecture is now a theorem in the unitary case. So that's the second of the conjectures. And the third, which is more or less completely open, is what to do with the first derivative of the tensor product L function in the center of the critical strip when the sign of the functional equation is -1. Now, we've seen that the sign being -1 means the order of vanishing is odd. So we're asking about the first possible non-zero term. And in that case, the adelic group that acts on this distinguished tensor product of local representations doesn't come from a pair of orthogonal spaces, because the Hasse-Witt invariants take a product to be -1. So there's no space of automorphic forms. And we can't even talk about a period integral. There has to be something that comes in that replaces the space of automorphic forms that we can use to study the first derivative. Okay, so I don't have a conjecture for this in general. This is the arithmetic conjecture, the most interesting one to me. But I only have a conjecture when the groups at infinity, at the infinite places of the number field, are compact. Both groups, the odd orthogonal group and the even orthogonal group, have to be compact. And then that means, for example, is that me or someone else? Good. And that means the number field has to be totally real, because you can't have compact groups at complex places. So we're only in the case where we're in a totally real number field, not a general number field like the global conjecture. And moreover, we have to assume that the branching is such at real places so that the real groups are compact. Okay, and I'm going to even assume more, namely, these would be representations of compactly groups, so they would be finite dimensional. I'm going to assume that at every real place, the representation, the distinguished representation, is the trivial representation. It makes it a little easier to state. And then the representation of the finite adelic group, which you ignore the real places, occurs in the middle cohomology of a variety called the Shimura variety, which is a product of the odd orthogonal Shimura variety of dimension 2n-1 by the even orthogonal Shimura variety of dimension 2n-2. And that's not just a complex variety, but it actually has a canonical model over this totally real field K. And we have a representation in the cohomology, either the de Rham cohomology or the L-adic cohomology. This representation of the finite adelic group is known to occur. Now, what we hope is that this representation also occurs in a Chow group of homologically trivial cycles of a certain codimension on this Shimura variety. That's not known at all. We know almost nothing about Chow groups. However, we can make such a cycle in this Chow group from the diagonally embedded Shimura variety associated to the even orthogonal group, because we have that diagonally embedded. And then if we take that cycle and we use the so-called Beilinson block height pairing on the Chow group, which is well defined, that gives us an invariant linear form that's like integration over the diagonal in the automorphic case. So to make this analog of automorphic forms, we have to introduce Shimura varieties, we have to introduce their Chow groups, we have to introduce the Beilinson block height pairing. And then the arithmetic conjecture is that the following are all equivalent, that the linear form, when you intersect against this canonical diagonal cycle, is non-zero on this component, that the derivative of the tensor product L function in the center of the critical strip is non-zero, and that this representation occurs with multiplicity 1 in the Chow group. None of these things are known. However, there's a refinement of this conjecture. If you can't prove anything, you just refine it, and it actually gives an exact formula for the first derivative in terms of the height of this component of the diagonal cycle. So is anything known? Well, yes. When we take S to be a curve, so that occurs when you're restricting from SO3 to SO2, The Chow group is exactly the Mordell-Weil group of the Jacobian. Divisors of degree 0, modulo rational equivalence. And the exact formula in this arithmetic conjecture, everything basically was established. And the exact formula was found by Zhou Zhang and his students in 2013. Really pretty much ended the curve case. But that's when the cycle T has codimension 1. T is a bunch of points on the curve. And codimension 1 cycles are actually pretty well understood. They have the Picard group, you have the Mordell-Weil group. That makes sense. The problem is that when you go to the next level of group, like restricting from SO5 to SO4 or SO7 to SO6, then you get into higher codimension cycles about very little, which is known. Now, Xiao was generalizing the formula that Don and I found in the very simple case when n was 1, where the totally real field was the rational numbers, where the finite idyllic group was split. Then S, the Shimura variety, turns out to be the modular curve x0 of n. And the cycle T is given by Hegner points, which are rational over the Hilbert class field of an imaginary quadratic field. To define an SO2 and SO3, you have to pick a quadratic field. And if we take the conjugate points in this cycle and we map them to an elliptic curve quotient of x0 of n, and it turns out that all elliptic curves are quotients of these curves, and we sum them up, we get a point in the elliptic curve over the imaginary quadratic field. So that's a complicated construction because at first it depends knowing something about this map from x0 of n to the elliptic curve, and then it involves addition on the elliptic curve. Nonetheless, Zage and I could prove the formula that the derivative of the L function of this elliptic curve at 1 was the volume of the period lattice, that's the integral of omega wedge omega bar for a non-zero differential, times the Néron-Tate height of this point, that's the size of the point or how much paper it takes to write it down, divided by the square root of d. And this formula was what got me started on this business. And soon after we proved this formula, Colli-Vangen proved the rank 1 theorem, which was when P has infinite order, and so that means the height is non-zero and the derivative at 1 is also non-zero, then the rank of the elliptic curve over the quadratic field is 1 in confirmation of the conjecture of Burchett, Swinnerton, and Dyer. Even better, he proved that Tate-Shafarevich group is finite, which was a real achievement. So that's what got me started on this. And if you look at this theorem, it involves elliptic curves and heights and modular curves, but it's not clear it involves any representation theory at all. And when I first started working on this subject, which was in the early 80s, I had absolutely no idea that it was related to representation theory. So I'll tell a little chat story about how I got into all this business with restriction of representations, et cetera. And it started when, here's a picture of Don Zage at the time we did our work and our paper. So Don, as people know, was a real prodigy in mathematics. He finished high school at the age of 13. He wanted to go to Oxford, but Oxford didn't take anybody who was under 16. So he went to MIT, and then he finished MIT in 2 years, and then applied to go to Oxford as a graduate student when he was 15. And they took him as a graduate student because there was no prohibition against taking graduate students who were under 16. He wrote a thesis in topology with Michael Atiyah, and then went to Bonn to work with Hirzebruch and really began his great work in number theory. And I met him when he came to Harvard as a distinguished visiting professor, and I was a second-year graduate student, and I was 1 year older than he was. So it was very discouraging, very, very discouraging. Anyhow, Don and I worked on this paper together, and we had pretty much finished the proof in the fall of 1982, and he had been invited to speak at a conference in Durham, England in the summer of '83, and to give 2 lectures. So we wrote to the organizers of the conference, which were Birch and Rankin, and we asked if Don could give 1 talk on this, and I could give his second. I could take his second talk. And Birch knew that we were working on this because I had been corresponding with him. And so he wrote back and said that would be fine. So the first day of the conference, Don got up and gave an hour where he summarized how you would ever calculate the derivative of this whoops, sorry, I'm giving away everything, the derivative of this L function, the left-hand side of this equation. And then I got up for an hour and I talked about how you might actually try to calculate the height of the Higner point, which is the right-hand side of this equation, but we couldn't do much in the way of details. It's a complicated computation. And we thought we were done, but of course, at the end of my lecture, there was a little committee that formed up in the front of the room with Birch and Rankin and Castles and Jean-Pierre Serre, and they hauled us up there, and it was like, okay, we want you to give one talk each on every day for the rest of the meeting until we see all the details of this. So that's what we did. We gave one talk every day of the meeting. It was completely exhausting. We were trying to write a compte rendu note at night. The whole thing was fun, but it was completely frazzling. And the last day of the conference, the afternoon was scheduled for graduate students and recent postdocs to give 20-minute talks, and what we would now call a poster session. And I thought that, given what I had been through in the last week or so, I was entitled to take a nap during this time, and I would rest up for the trip, go home. And fortunately, I announced my plan to take a nap over lunch to my friend Marie-France Vigneras. And she said, no, I could not take a nap because I had to go to at least one talk that afternoon. And one of her graduate students was very strong, and I would really enjoy his talk probably. And she just wanted me to go and see him. So I very reluctantly agreed to go along with Marie-France, sat in the back of the room, was prepared to go to sleep. And then that student of Marie-France happened to be Jean-Luc Waltz-Purgé, one of the greatest mathematicians I've ever interacted with. And certainly, I think the person who's done more in the theory of automorphic forms of anybody since Robert Langlands. Anyhow, he was just a little postdoc at the time, and he spoke on this paper sur les valeurs de certaines fonctions L automorphes en leur centre de symétrie. So the values of certain automorphic L functions in the center of their symmetry. And I have never been to a more electrifying talk in my entire life, and it lasted maybe 15 minutes because he didn't have much time. And he described how he found this formula for what I would call the global conjecture for SO3 to SO2. And you can see in the bottom of this page, that's one of his period integrals. And it was so electrifying because I could see that Waltz-Purgé was studying exactly the same L functions that Zaghi and I were. And the only difference was he was studying their value in the center of the critical strip, and we were studying the first derivative. But his perspective was infinitely more sophisticated than ours and opened up a whole avenue for me of generalizations, even in the SO3 to SO2 case, on Shimura curves, etc. And I mean, I just went back, I flew back, and by the time I arrived in Boston, I could incorporate Waltz-Purgé's point of view into our point of view, and it was just completely exhilarating. And then I decided I better learn some of this representation theory he was using, because this paper is just an absolute triumph. And then the next year, and just to continue the story very briefly, the next year I gave a course. I had just arrived at Harvard, and I gave a course on this work of Waltz-Purgé and quaternion algebras and quadratic fields and Shimura curves and all I thought I knew. And I had this young student in the course who had just arrived from India, Dipendra Prasad, and he knew a great deal of representation theory, and began to think about generalizing Waltz-Purgé's local and global results to what are called triple product L functions. And although we didn't understand it at the time, that was restriction from SO4 to SO3. And then the story just continued, and everything was, in my opinion, very serendipitous. I bumped into Steve Rollis at just the right time. I bumped into David Vogan at just the right time. And it took really 10 years to put the conjectures together. So if you want to read a little bit more about sort of how this all evolved, and I don't want to suggest that it was all systematic or linear or anything. It wasn't. I mean, it was mistakes and guesses, etc. But I wrote a little bit of a historical paper called The Road to GGP, which you can find on my my webpage under the ePrints thing. I just keep posting like that. I'm not an archive person. And it'll give you an idea, I think, of how these connections, which at the time, I mean, as I say, I didn't know any representation theory at all. And it was a great way to learn about the work of Langlands and Vogel and Waltz-Breguet and many others. And the reason I think it's exciting is when two subjects touch on each other, like number theory and representation theory, you can really make guesses in one subject from results in the other. And that's how all of these conjectures really evolved. And I hope by giving you this talk, I've given you some idea of sort of what the conjectures are, but it's easy to read more details about them in the literature and some vague idea of how we got started on them. So at that point, I'll just say, thank you very much. Here's some more spherical harmonics, and I'll be happy to try to answer questions from the talk. Thanks.